All right, so we've known for a long time that some chemical species have charges on them. You have positive ions sometimes that have a plus number attached to them, and you have negative ions that have some negative number, meaning they've picked up some excess electrons. And there are a lot of things that we say are neutral or that they have no net charge, like I'm using water as an example, where there is no charge written on them, and we say that that means there is no total charge. Sometimes we just say there's no charge. But it would be more accurate to say that there's no net charge because there are charges inside and they're what's holding these structures together. If you have a water molecule, inside it there is an oxygen atom which has pretty much acquired two extra electrons from the hydrogen atoms. They're technically sharing them, but oxygen attracts those electrons much more strongly than hydrogen does. And so we say that the oxygen in a way has a charge of -2. It's got two extra electrons. And the hydrogens, which have pretty much lost those electrons, could be said to have charges of +1 because their electrons that they're technically sharing with oxygen, oxygen is hogging them. They're spending most of their time with the O, very little time with the H they used to belong to. These numbers that I've put up, we generally avoid calling them charges, although people will use that term by mistake, and I probably will too. But the term that we like for this is oxidation number or oxidation state of an atom. So in here we could say that the oxidation state of the oxygen is -2, the oxidation states of the hydrogens are both +1. And if you add these up, you get that zero that we were expecting. When we say that water has no net charge, there can be a lot of electrical activity going on inside with electrons shifting towards certain atoms and away from others, but the total in this case has to come out to zero. And in some cases, to figure out what's happening in a redox reaction, we have to look in detail at what are the oxidation states of these atoms and how much did they change during a reaction. So we're going to look at how to do that. We have a list of rules for you here that explains how to find oxidation states, and it's 6 rules, which seems like a lot when you first see it, but let's go through them kind of quickly. And I want to show you that at least a few of them, the first 3, are pretty obvious. You probably would have guessed them anyway, and then we'll do some practice and see how to apply them. The first one's very easy. The first one says if you have a pure element, let's say you have a lump of iron, Fe, this doesn't look like it has any charge on it, and so we say its oxidation state is 0, which, okay, you're probably not shocked. Next, if you have a monatomic ion, something like a chloride or a sodium ion, the oxidation state of that is exactly what you'd guess. Chloride has an oxidation state of -1 because it says so right there. Sodium ions have an oxidation state of +1, and there it is. So, again, pretty intuitive. The oxidation number for hydrogen, if you look at hydrogen on your periodic table, one that has the charges on it, it should tell you that hydrogen is usually +1, but is capable of being -1 sometimes. And that's what Rule 3 says. It says the oxidation number of hydrogen is +1, except in some rare cases, usually grouped with an alkali metal, where it can flip to -1. In 4, they start getting a little less obvious. The oxidation number of oxygen is -2, which is what the periodic table says, so no surprise yet. And then they say, except in peroxides, which are compounds where you have 2 oxygens bound to each other. In that case, they tend to be -1 each. And in some fluorine compounds, fluorine is more electronegative than oxygen is, and so it can throw off the oxidation number of oxygen sometimes. And these next 2 about the more electronegative atom, these will come up when we're doing our examples, and we'll get into them in more detail then. I don't like talking through 5 and 6 right away because they're kind of general and they're easier to illustrate when we have an example in front of us, so let's get to that. The first thing they ask us about here is H3BO3, boric acid. H3BO3. So when you're solving one of these, the strongest rule is number one, and you try to apply that first. Once you've done that, or if it doesn't apply, you go on to rule two, rule three, and so on. And by the time you get to the end, you should have an oxidation state worked out for every atom in your compound. So this starts with a pure element. There are no pure elements in here. So rule one is irrelevant. On to the next one. The oxidation number of an atom in a monatomic ion. This is not a monatomic ion, so that doesn't matter to us either. The oxidation number of hydrogen, okay, now I'm listening, is +1, except in metal hydrides, which this is not. So each of these hydrogens has an oxidation state of 1, which means there's a total of +3 here. I'm going to say +3, and I'm going to say +1 each. Some people like to work with the total numbers. Some people like to work with the per atom numbers. I'm neither. I try to put both because we can ask about either one. We can ask what the total charge is from the hydrogen, or the total oxidation state, or the oxidation state of an individual atom, so I prefer to be ready for either thing. So, rule 3 covered our hydrogen for us. Rule 4 says the oxidation number of oxygen is -2, except in peroxides, which this isn't, and in fluorine stuff, which this is not. So all these oxygens are -2s. 3 -2s is a total of -6, and up here I'll put -2 each. Okay. Now, rule 5, the more electronegative atom is not relevant to us here, but rule 6 says the sum of the oxidation numbers of all the atoms in a molecule has to equal the charge of that molecule. This whole thing, because it doesn't have a charge listed, is considered to have charge 0, which means all the oxidation numbers in it must add up to 0. We got the hydrogen covered. We got the oxygen. For the boron, you can put an X, or I'm going to use letter B. We don't know what the oxidation number for boron is, but it has to be something that will make the total come out to 0. Now, you could probably just eyeball this and see that this boron must be +3, because that would bring our total up to 0. If you don't like eyeballing it like that, you can make an equation out of this and say +3 from the hydrogen plus B, which we don't know, plus -6 from the oxygen adds up to 0. And then you can do algebra to that, and soon enough you will find boron must be 3. If you ever have a really complicated formula, or if you're just tired or flaking out a little bit and can't remember how to do this, it's nice to know that you can do it with an equation and get the solution. But most of the time people can just eyeball these. They'll say 3 minus 6 is -3. Okay, I need a +3 to make the charge work. So for this, they're saying, what's the oxidation number of the underlined atom? That would be boron, and its oxidation state is 3. Probably better to say +3, just to be unambiguous. So let's see if we can do some others a little bit faster. CH4, pure element, no. Monatomic ion, no. Hydrogens are +1. So the hydrogens combined add up to +4 here, but the total for the whole molecule is 0, so the carbon must be -4. Fair enough. Next one is the bromate ion, BrO3-. So, pure element? No, it's not. Monatomic ion? No, it's a polyatomic ion. Hydrogen atoms don't have any. Oxygens are -2. So, 3 oxygens, there's a total of -6 coming from the oxygens. What does that mean for bromine? If there weren't a minus here, if this were just BrO3 and it was a molecule, then the bromine would have to be +6. But here they're saying the total for this whole collection is -1. So we're down at -6. The bromine has to bring us up to -1. The bromine, in this case, must be +5. +5 plus -6 makes our total of -1. So for this one, +5 and minus 6 total from the oxygens. Next one, sulfite, SO3 2 minus. Pure element, none of these matter. Oxygen is often where we start off with these. 3 oxygens means minus 6. Our total has to be minus 2. So in this case, the sulfur must be plus 4. Bicarbonate or hydrogen carbonate, HCO3 minus. No pure elements, no monatomic ions. Hydrogen is plus 1. The oxygens are minus 2 each, so total of minus 6. What for the carbon now? What do you think? These two together put us at minus 5. The carbon has to bring us up from there to minus 1, so the carbon's oxidation state must be plus 4. In other words, I'll do this one with the formula just in case you want to see. Hydrogen plus carbon plus the 3 oxygens, which are negative 6, all together add up to negative 1. Add up what's on the left-hand side, you get C minus 5 equals negative 1. Take 5 to the right, C equals 4. All right. Nothing too bad yet. MnO. Well, oxygen has to be minus 2. The total is 0, so manganese must be plus 2. Hydrogen peroxide. Remember this one? Hydrogens are plus 1, so plus 2 from the hydrogens. If oxygens were minus 2, we'd be in trouble here. We'd have plus 2 and negative 4, and that wouldn't add up correctly. But in peroxides, oxygen is only minus 1. So in this case, we have each of the oxygens is minus 1. There are 2 of them, and so everything works out. VO2, vanadium oxide. Well, the 2 oxygens must have a charge of minus 4. The total, though, is plus, as in plus 1. So the vanadium has to bring us from minus 4 up to plus 1. It must be vanadium 5. Nitrous acid, HNO2. Each oxygen's minus 2. I'm sorry, the first rule is that hydrogen is plus 1. Then the oxygens are minus 2 each. It isn't really important that you do them in order, but I'm trying to do them in order because in some case one rule will override another. So I should try to do it right. Plus 1 for the hydrogen, minus 4 for the oxygens combined. Now, what do you think for the nitrogen? The total charge on this thing is 0 because they didn't mention any charge. 1 plus negative 4 puts us at minus 3, so the nitrogen must be a plus 3 to get us to where we need to be. C2, whoops, sorry. Subscript, C2O4. Oxalate. Oxygens are minus 2 each, so there's a total of minus 8 charge from our oxygens. We need to get up to minus 2, which means the carbons must be providing plus 6 or plus 3 each. With questions like this where there's more than one atom, please be clear about what you're doing. Please either say that there's a total of plus 6 from the carbons, both of them, or I prefer to say the state is plus 3 each. Each carbon has an oxidation number of plus 3. If you just say 6 or if you just say 3 and you don't explain it in any way, then you're giving an ambiguous answer, and that may not get you all the points if you're talking about a test question. Xenon tetroxide, that's an unusual one. You don't often see noble gases reacting, but they can. Okay, oxygens are minus 2 each, so we have a total of minus 8 charge from the oxygens. The xenon must bring us up from -8 to -6, so the xenon's oxidation number must be +2. Sodium hydride, not a pure element, not a monatomic ion. The oxidation number of hydrogen is +1, except in metal hydrides, where the oxidation number of hydrogen is -1. So this is a case where these two atoms show up and the hydrogen says, okay, I'll be +1. The sodium goes, well, wait, I'm +1. And the sodium says, and I don't really know how to do anything else. I'm always, always, always +1. The hydrogen says, well, okay, I guess I know how to be -1. I don't do it very often, but if I do that, and the sodium does that, then we get a total of 0, and that's what we need. If these both showed up and tried to be +1s, then we wouldn't get a neutral compound. For S2O6, let's see, 6 oxygens, that's a total of -12. The sulfur has to bring us up from -12 to -2, so the sulfurs must be delivering +10 total. And +10 split up between two atoms means each sulfur is +5, so I'm going to put +5 each. This is another one where you have to be careful about your answer. Either say, probably best to say each individual sulfur has an oxidation state of +5. And I wouldn't even know what to call this. It's some xenon compound, and because they react so rarely, there's hardly even a system for naming them, but that's okay. We'll just call it that xenon thing. Well, pure element, no. Monatomic ion, no. Hydrogen, +1. Oxygen, -2, with rare exceptions. The xenon, where are we now? 1 plus -2. We're sitting at -1 right now, so the xenon must bring us up to 0. So the xenon's number must be +1.